I thought I'd make a quick video. Well, I don't know how quick it'll be, but it'll demonstrate how we can use the idea of vector components to make an addition problem much easier to do. In fact, I'm going to show one that really any other way would be just about impossible. So let's take a look at the problem. What you see on this screen is a description of 4 different vectors in 4 different directions. And we just might imagine somebody is taking a walk, and they walk vector A, and then B, and then C, and then D. So I've listed them out with their directions. And then what I've done is I've shown what this would look like on a map using our head-to-tail vector addition method to see if maybe we could just connect these 4 vectors head to tail and then draw in the resultant and get the answer that way. So the only thing I have to draw here yet is the resultant, which goes from where we start to where we end. We got an arrowhead right in that direction, and then you see what we have. We have a 5-sided figure, and it's not a regular 5-sided figure, and there really is no good math other than components that we could use for this. So I'm going to demonstrate here on this diagram that the idea of using components, and this is something that probably a lot of you would maybe intuitively do. So if we retrace the steps here from start to finish, and I'm going to use green, we walk along vector A, and then we could walk along vector B. Now those are fine just as they are because they're already east and south. But instead of walking at a direction called 210 degrees, which is along the direction of vector C, suppose we instead walk the southward part of that motion first, and then we walk the westward motion, and we have done what is equivalent to walking along path C. Now those 2 green vectors that I just drew there are the components of vector C that we will find in the next diagram, using another diagram, what those are. And then we pick up where we left off there with that horizontal component, and we walk another westward component of D, and then after that we walk straight northward. And so these last 2 vectors here are the components of vector D. So we have 2 vectors here that are not already in convenient directions like east, south, north, and west. So if we take those 2 and we separately divide them into their east, west, north, south components, then what we're going to do is just do the addition with the green vectors. And of course this is a kind of problem that you've already done in practice in class as part of your mop practice. So then it'll be back in more familiar territory. So on the next slide here we'll take vector C, and I'll show you how we use trig to find its components, and then we'll follow that up with vector D. Well, here is vector C. It is described as 136 meters at a direction of 210 degrees. So I'm going to go back up here to its tail and put myself in a little coordinate axis just so I can remember 210 degrees, which is another name for 30 degrees past 180. Now I'm going to draw the components right onto this coordinate axis, so I'll extend it across the page like this, extend this one down like that. Notice we're working down here in the 3rd quadrant, as they call it in math, and so I really don't need to see much of the other 3 quadrants. And so I'll use green like we were before for the components. And again, the idea of components is you go back to the tail of your vector and say, alright, instead of walking 136 meters in a southwest direction, what if I just walk the south part of it first for as far as south as I'm going to need to go, and then I'm going to stop, put my arrowhead there, and that is what I'll call my southward component. And then I'm going to draw the westward component from there. Now I could have certainly drawn the westward component first. In fact, in this case it might make more sense because I've labeled that angle up there 30 degrees, but I could just as easily label this angle down here 60 degrees and use it. So now it's time to do a little trig. And we got to remember, right triangle math says if you know the hypotenuse and the angles inside your triangle, of course it has to be a right triangle, so I'll remind you of that by putting the little square thing here. Then to calculate the legs of the triangle, you use the sine and cosine functions. So this vertical component here is found by taking the hypotenuse of 136 meters times, now I'm going to use the 60-degree angle. You could certainly use a 30-degree angle inside this triangle too, but because my side here is adjacent to 60 degrees, I'll use the cosine of 60. Make sure you're in degree mode if you're doing this yourself on your calculator. And that gives us gives us 68 meters. I'm going to write this just as a reminder, south. Now, of course, it's south because I've drawn it with a southward arrow, but I'm going to need that a little bit later. And then I'm going to do this horizontal component over up here, which is opposite the 60 degrees. So my math says if I take the hypotenuse times the sine of 60, if you're using 30 degrees, it would be adjacent, so you'd use the cosine of 30. And that gives us 118. And I'm going to write here, just as a reminder to myself, that this is west. Okay, so there's the components of vector C, and we'll come back and get those a little bit later. Now we'll move on in another diagram to do vector D. Now if you're drawing this along with me, I just want to encourage you to not try to fit vector D on this same diagram, but to start with a fresh little coordinate axis and draw it there. Alright, here is vector D, drawn as it was on the original figure, which you can always rewind and look at. It was described as 183 meters at 120 degrees. So I'm just going to mark, because it's convenient here, that that is 60 degrees above 180. I could just as easily call that 30 degrees beyond 90, and I would be labeling the other angle. So its components, if we start here at the tail, I could go upwards and leftwards, or that would be north and west on this kind of orientation. But I think because I've already got it drawn, I'm going to draw my westward component first, just as far left or west as my original vector goes, and then straight up from there in the northward direction. Make sure you put nice big arrowheads on there. I like to work in different colors, and I encourage you to do the same. That way you can see the difference between your components and your original vectors. And now, since I have the 60-degree angle marked, I'm going to use that to refer to my sides. So this short horizontal side here is adjacent to 60 degrees. So I take 183 times the cosine of 60. There's no hard and fast rule when you use sine or cosine, except for if you're finding the leg that's adjacent to your small angle, you make sure you use the cosine. And if you're finding a leg that's opposite or not touching that angle, you're going to use sine. And of course you'll never use sine or cosine of 90, because we have to use one of the acute angles inside the right triangle. So I did this previously on my calculator. Gives me approximately 91 meters. And I'll write the word west. And then the other component, 183 meters times the sine of 60. And that equals about 158. I'm rounding just down to the ones place here. Keeps it consistent with all the other numbers that I have. This one is, sorry, I think that got chopped off. This one is north, is what I was saying before my hand hit the wrong button. So now we have broken every vector that we need to into its components. If you need to stop and review this triangle math again, I encourage you to do that, because what's next is I'm going to put all of this back together again. Alright, so here's those original four vectors. I've left their names A, B, C, and D off of them, just for a little space. And what I've done here is I've written down, for the two that we broke into components, I've written down the two vectors for each one that will replace the original one. So I'm literally just forgetting that these vectors ever existed. So now I have, instead of 4 vectors, I really have 6. We just take an accounting real quick. We've got the 2 original ones that did not have to be broken up. That's 1, that's 2, and then we've got 3, 4, 5, 6 for those 4 components there. So we're going to assemble these all back together again. So what's the logical way to do this? Well, we want to do vectors that are in similar directions together first. So my first vector is an east vector, 88 east. So I'm going to combine that with the west vectors, but leave out the south and north ones for now. So we've got an 88 east, but we've got a whole lot more west. So how much is that? If we have 88 east, 118 west, and another 91 west, that's 88 plus actually I think I'm going to subtract here. Let me change this. See, I don't have any more east, so I'm not going to add anything to it. I'm actually going to subtract 118 and then subtract 91. I could have certainly written this in the other order. I wrote the east one first as a positive. Well, what that gets me is 121, and because that number came out negative, that's what I called all my west vectors. I think probably in hindsight a more logical way would be to take the west ones, 118 and 91, and put those together, and then just subtract the east one. But we've done enough vector addition with similar directions that I think you can see how I got 121 west. Now I'm going to deal with the north-south ones. Be a little smarter about this. I noticed that my south vector is the 2 vectors that are south more than overcome the north vector. So I'm going to add those together first. So 272, that's a south vector. Add that to another 68 meters south, and then I'll subtract the 158 to the north. And that gets me 182. And remember, this was more south than north. So now, instead of having 6 vectors, which I had a moment ago and I marked in red, now I have 2 vectors, 121 west and 182 south. I'm going to get myself a little more space, and in fact I'm just going to get this stuff off the screen that I don't really need, because all that preliminary stuff was just meant to get me to this point. How do we add 2 vectors like this? I think I'm going to switch colors here. 121 west, which would look like this, added to, which means head to tail with, 182 south. Notice I'm going to draw 182 longer than I draw 121. It's about 50% longer. Don't use a ruler for any of this. And then I'll have a resultant. How about a color like lavender for the resultant? And that right there is ultimately what we were looking for. Notice that's the exact same direction that the original resultant was that I drew back on the first screen. So now we've just got one more, or actually I guess 2 more math steps to figure out how long that is and what direction it's pointing. So Pythagorean Theorem tells us how to find the magnitude of r, its length. That's the square root of 121 squared plus 182 squared, which is approximately equal to 218. So that's how many meters that represents. And then we need the angle. When I have the 2 legs of a triangle, I like to use the inverse tangent function. The inverse tangent of opposite side, what's across from that angle is 182, and the adjacent side is 121. This gives us a 56-degree angle, which, again, this is where a lot of you get stuck. You're good with this right triangle math, and then we've got to describe what this is. So I'm going to run through this maybe a little more carefully because I've seen you have problems with it. This little arcy thing here that I just highlighted in blue, that describes how far my resultant vector is, the lavender one, from the red vector above it, the 121. Well, what direction is that 121? That's pointed westward, or what we call 180 degrees. So if we count counterclockwise from a 0, we would go all the way around to 180, And I'll just model this here in blue. That's 180, and then another 56, for a total of 236 degrees. So putting it all together, I'll circle my final resultant. 218 meters, pointed 236 degrees, and that means counterclockwise from 0. So there's the full-blown process. Now, you saw me do this with 4 vectors, 2 of which were already in convenient directions, and we didn't need to break them up. But you really have no limit on how many vectors you can add together with this method. It's just a matter of, I guess, how much time you have to do drawings and break them into components. But it's a very versatile kind of a skill, and it kind of uses a little of everything that we did in this vectors unit. So I'll leave it at that, and of course, if you have any more questions or things you want to clarify, you know where to find me in the classroom.